Good afternoon, everybody. Welcome back to lecture number 12. Today we will continue our discussion regarding the condenser and what is the job of the condenser and the synchronous inductor to improve the power factor. So here, if we note from the power factor control, or we call it the V curve, is by just changing the excitation voltage, I can control the magnitude of the armature current, and the angle of it with respect to Vt. So I can have Vt Ia control by just changing the excitation voltage at this bus. So for example, if you're underexcited, if you run it as an underexcited synchronous motor, you will be at a lagging power factor, but it's lower, it's high Ia. Up until you reach normal excited, you get the smallest magnitude of Ia, but your power factor is 1. Then if you become overexcited, your Ia becomes leading, and now the whole synchronous motor would act as a capacitor. So this is very important application in real life. And here is the representation. If Ia is 90 degrees leading, then If will be in phase, so torque angle is 0. What's the power factor of the motor? 90. No, 0. 1. Cosine 90 is 1. What is the power factor in this case? What is the power factor for the synchronous condenser? It's cosine of angle of Vt minus angle of Ia, which is 90. Cosine 90 is 0. What is the power factor of the synchronous inductor? It's cosine of 0 minus 90, which is minus 90, so 0. However, here in these two applications, if you notice that if you become all the way, the largest amount of Ia, all the way you reach to 0. But this is just for pure synchronous condenser. The moment you connect it to the grid, you will have an angle of Ia. Get it? يعني هو as a synchronous condenser standalone, it will be 90 degrees Ia with respect to Vt. The moment you connect it to the condenser, it's a function of nearby loads. Get it? So this Ia will be somehow like that for the whole system. And last time we solved this part A, correct? We did not solve part B. So to solve this part A, let me repeat again the problem again. So a 3-phase 5 MVA, this is rated apparent power, 11 kilovolts, that's line to line, 60 hertz synchronous machine with 10 ohms excess per phase. The machine is connected to rated bus, which is same line-to-line voltage, same frequency, and is desired to operate as synchronous condenser. So if I say synchronous condenser, it means what's the real power?
0.
Yeah, no load. So here it says neglect rotational losses. If you neglect rotational losses, I'm sorry, what's the, here's the correction. What's cosine 90?
0.
0.
Yes.
Okay. So here, we are operating at normal excitation. Normal excitation, it means the angle between Ia and Vt is 0. So cosine of theta is 1. For find the stator current, draw the phasor diagram. To solve this problem, the real power is 3 Vt Ia cosine theta. For normal excitation, we have the power factor is 1. So if you equate this to 0, Vt is not 0, cosine theta is not 0, then Ia has to be 0. So if we neglect all the rotational losses, we do not draw any current. So Ia will be in magnitude 0. So EF would equal to VT. كأنها open circuit, كأنها V definite. Clear? And it's equal to 11 over square root of 3, which is 6.35 kilovolts per phase. Now, if the excitation voltage is increased by 150%, it means you multiply this number by 150% of the normal excitation. Now I increased IF. So initially we were operating at normal excited with IA 0 because there is no load. Now I increase IF. So if I increase IF, I'm going to be in the under-excited. Keep in mind, this IA is not 0. There is load here. If there is no load and you neglect the losses, this IA2 will be 0. Get it? So now, how to solve this problem is very easy. Because the power transfer is 0, we have delta is 0. So the torque angle is 0. If the torque angle is 0, I substitute Vt the same, 65.1 minus 1.5 times that. Both of them are in phase. Divided by Jx of s, and now I get a new Ia, which is 90 degrees. Ia now is what? 90 degrees. So this is a pure synchronous condenser. What's the power factor of pure synchronous condenser?
0.
0. Is it connected to a load? No. Are we neglecting losses? Yes. So because we are not connecting it to a load and we are neglecting the losses, the phasor diagram becomes purely synchronous condenser. The moment I connect the loads, things will change and I will have actually different magnitudes and angle. The last part is if it's decreased by 50%. Repeat. Again, torque angle is 0. Because torque angle is 0, I repeat everything here. 6351 minus 0.5 times that over that. I get now IA to be 3177. It's the same magnitude, if you note. 31755, but one is plus 90, one is minus 90 degrees. So again, part A, B, and C, because we neglect rotational losses. If you recall in E360, your input power, you start with some losses and then you get the air gap. You remember that? What was this block? You supply power to the stator or the rotor for synchronous motor? To the stator. So here we have stator losses. What are the stator losses? Copper, core, hysteresis. So all of them we lump them together, we call them rotational losses. Why we call them rotational losses? Because those are the losses that have, even if I don't have any load connected, they're going to still occur. And those are the ones that we ignore in part A, in part 1 of the problem. So the air gap power later translate into rotor copper losses. And then this is P output, or the shaft torque. Now if you want to include friction, you can say friction minus shaft, but let's stop here. Clear? So in part 1 we ignore this. Now we have to consider them again in this part to be what? If rotational losses means any losses in the stator part for our synchronous motor are 80 kilowatt, adding 80 kilowatt, what does that mean? It means if my output power is 0, and let's say we say everything here is 0 in the rotor side. In part 1, this is 0 plus 0, so input power is what? 0. So now input power is not 0. Input power actually equals to rotational losses. Because there is no load, there is no air gap power. Clear?
Yes.
Think about it. In part 1, if we ignore these losses, there is no air gap power because there is no load, no mechanical load. Your input power is 0, and this is part 1. This power, input power is 0. But now we equate 80 kilowatt to this quantity. And this is what we do in this part, where we equate 80 kilowatt to 3 VT IA cosine theta, and now I'm getting 4.2 amp. Because my power factor is 1, my VT is 63513, and this is 80 kilowatt. So this implies in part 1 I have IA to be, in part 1 IA2 was 0, in part 2 IA2 is 4.5. So now if I'm normally excited 4.5, I'm going to get a certain EF. And I'm going to repeat overexcited and underexcited the same. So how to solve this problem? You have to calculate EF, which is VT minus JIAXS, which would equal to this number. And clearly, VT and EF now are not in phase. Now, this is not a mistake. It's just rotated. But I told you to draw it better. It's better to have VT at reference 0, and then EF to be like that. And this quantity is JXSIA. So what is your IA? Your IA is 4.2. And it's 4.2 on top of VT. Why? Because we are normally excited. So excitation has nothing to do with delta. Excitation has to do with the angle between VT and IA. When delta becomes in the game if there is a difference in angle between EF and VT. So EF is VT minus JXIA. Get it? So that is very important to consider. Okay? So this is more real life application. And if you do this part, he's only asking you to do it for normal excitation. This is EF, which is 635 minus J 4.2, converted to magnitude and angle. If you do magnitude and angle, it's going to be 6351 minus 42J. So your torque angle is minus, so your delta is minus 0.4 degrees. Clear? That's a very small, if you count rotational losses, your delta is almost 0. So that's why you can safely ignore rotational losses for synchronous condenser. So when you work with the job that you will get from our friend with the solid electricity company, and they ask you to calculate the synchronous condenser, always you can safely assume ignoring rotational losses. Because rotational losses are 80 kilowatt. For a big machine 80 kilowatt يعني كأننا موصلين for a mega, what's the rated capacity? For 5 mega 80 kilowatt is peanuts. So you can ignore it. Having said that, do we care about it in real life? So I don't think I will ask you this in the exam. I'll say with 90% I'm not going to ask, but there is still a 10% chance that they'll ask. Maybe that's the A+ question. Okay? So, I have posted practice problem 1, practice problem 2, practice problem 3, and practice problem 4 at the end of the slides. We'll try to solve them later, okay, if we have time. But now we are somehow late. Let's focus on the material itself. The other concept, which is, I think, very important in real life, is the dynamics of the synchronous generator. So do you remember this equation, the swing equation, when I subtracted the torque? It turned out that if I calculate the torques of my synchronous machine, it might not be very, very accurate, or I may not have access to the shaft. So not all the shafts you can connect a torque meter to them. So instead, how about if I find another equation where I just relate mechanical power minus electrical power with another quantity? And this is what we're going to do in the dynamics of a synchronous generator. So again, swing equation, it's relating rotational masses to the generator electrical parameters. Rotational masses to the generator electrical parameters. If you look at here, the inertia times the acceleration squared equals to the applied torque, which is mechanical minus electrical. So J is moment of inertia to represent the mass of the machine. Theta m is the angular displacement of the rotor with respect to stationary axis. T is just time, dt is regular time in seconds. And Tm is mechanical or shaft torque supplied by the prime mover. This is what your diesel prime mover gives you, the mechanical thing that rotates the machine. And this is the electrical torque. The electrical torque that is counteracting the mechanical torque applied. I told you, if you apply a mechanical rotation, there is some electrical torque that's counteracting it. We reach steady state if the torque is zero. The difference between them is zero. It means whatever you're applying, you're generating it in electrical. And this is the net accelerating torque. This is the accelerating torque. So if TA is 0, we have 60 hertz, steady state. Mechanical equal electrical. This corresponds to point A in the stability curve. If it's positive, it means speed will increase. So we're increasing the speed because mechanical is larger than the electrical. If it's negative, we are decelerating, so speed will decrease. Now what's the proposal is we introduce another quantity called H constant. And surprisingly, its unit is seconds. So this is a time quantity. And it is preferred over M for many reasons. One of them is it's from 1 to 10. Usually typical values are from 1 to 10. And 2 is if I write it down, I can, instead of calculating torque difference, I can calculate power. Power is easier to calculate than torque. So the H is defined as the stored kinetic energy of synchronous at synchronous speed, which is half J omega S squared. This is from physics 102. Oh no, physics 1? No, I think 102. 102, not 101. This is from physics 102, the first part, before you go into the electric. And the divided by the synchronous generator rating. So its unit is in second. So the swing equation now becomes like that, which is the difference in power, where delta T, d delta over dt is the difference between the angular speed minus the synchronous speed. Okay? So the derivation is provided for your reference in a separate Word document. So make sure that you read it. So this is the derivation of all the equation. We start from the old material. And then this is the swing equation. These are the parameters. So if you define theta as omega t plus delta, and you do the substitution, you take the derivative of the two sides, you take the second derivative, and then you will have, you start with this equation and you resubstitute everything, you will reach out to this equation, which in turns, if you divide h is half m s, then you will reach to this equation, 2h over omega delta, okay, 2h over omega s, d omega dt is b. We're not going to worry too much about it, but these are the equations at the end. So try to read this document, and explore it. If you have any question, let me know. So going back, so this is the equation that matters, okay? So the plot of delta versus time yields the swing curve. If you plot delta over time, that's a swing curve. Stability of the power system can be assigned or determined from the plot of all machines in our system. And every synchronous generator, it should have a parameter H. If you go open your homework and go inside the synchronous machine, there is the parameter H in your synchronous generator. So try to explore it. The mechanical input power PM is the swing equation is considered constant because conditions the electrical network can be expected to change before the control governor can cause the turbine to react. So the mechanical input power in the swing equation is always can be assumed constant because the electrical grid would try to stable the machine itself. If you connect one generator to the grid, would the grid impact the generator or the generator impacts the grid?
The grid will
Grid.
impact it.
Grid will try to reject it from the system unless it's synchronized. Okay? So if the accelerated power is 0, then the electrical equal mechanical, this is a steady state. And the changes in the electrical power, they come from the grid itself. So if there is a fault, if there is additional load, your PE would increase. If PE increase, your prime mover controller need to adjust and increase in order to reach the 60 Hertz, the stability. Get it? So it's not the other way. It's not you just increase the mechanical. No, for every increase in the mechanical power, you have to observe the electrical power in order to reach the steady state. The solution of the swing equation is very difficult. This is very difficult. If you try to solve it. So, and the problem is because it's difficult, because it's nonlinear and it is connected to the infinite bus. So we will ignore the dynamics, and next lecture we will solve a simple example illustrating this constant of H. Okay? Any other question? So homework is due today. Are you okay with that? Stop the recording.